Okay, yes. First, I apologize for not being in person. I tested positive like 24 hours for COVID, 24 hours before traveling, but so I couldn't go. But as I mentioned, I had the Indian visa and I have a voucher for the ticket, so I will try to see if I could visit sometime soon. And so my understanding is this is a group of graduate students or advanced undergraduates. So I'm trying to be pedagogical and hopefully say something which is not complicated, but is not also usually what you see in graduate school and is useful for the talks, understanding some of the talks next week. Please interrupt me for questions, well, obviously about the physics, but also let me know if there is any problem with the audio or something is not working. Let me know so we can try to fix it. Okay, so I'm gonna start with some remarks which perhaps are somewhat vague, but that kind of give you the idea of what I'm interested in for these talks. And one is the idea of, as I say, it's somewhat vague, but that you can call a rigidity or a uniqueness of some mathematical structure or some theory. And a very trivial example is suppose you have a crystal. So if you have a crystal, you have a very large number of atoms, but the positions are determined by a very small number of parameters. So that if I look at the crystal in just a corner, I can see the position I can compute the position of all the atoms. And that's different, for example, from a liquid or something like that. The idea I want to illustrate is, for example, like this similar thing are integrable theories. Integrable theories, you have, again, some sort of rigid structure that you can use to solve the theory by looking at ways which are not the usual way. For example, normally in a quantum field theory, you have to sum an infinite number of Feynman diagrams, but if there is an integrable theory, you have alternative ways to compute. Another example are analytic functions. So if I have a real function of a real parameter, you can, suppose I have some function, I can locally deform it and it's still a good function. But if I have an analytic function in a disk, changing the function in any small region changes the function everywhere because, yes.
Martin, you were able to draw a circle with your cursor, but are you trying to draw more with the cursor because it's stuck?
No, I just draw something like a little blob inside.
But your cursor is not moving. Is that because you're not moving it, or can you move it?
Let me see. Is that moving?
No, it's not moving.
Oh, okay. So, I mean, I can see it in my screen, but
Well, I don't know how to fix it at present. It probably is not causing.
let
Oh,
me
there it
see. I'm
is.
moving. Did I move the slide up?
Oh, now it's moving outside the screen. That's fine. Now move it.
Okay. So let's continue. Yes. Thank you for.
What?
Yeah. So no, what I was saying then, just in words, is that if I have an analytic function and if I change it locally, it changes everywhere. So it's another example of a rigid structure. If you have such a structure, then
Hello, Martin.
Yes.
Maybe you unshare it and share it again, the screen.
Okay, so let me close it. And let me open a new whiteboard.
From our side.
I draw a line, wavy line. Can you see
Yeah, we
that?
can see. Yes. Maybe draw something
Okay.
more.
Uh,
Yeah, we can see. Yes.
Okay.
Okay.
I'm still alive. Okay. So the idea is that you can find the solution if you enumerate a list of constraints that the solution has to satisfy. And sometimes this gives you a space of possible solutions. And your structure, your solution you want to find is some distinguished point in that space of solutions, or maybe you just find a unique solution to the set of constraints. The property we are interested in today is are called positivity constraints. So sometimes some quantities by physical reasons or mathematical reasons have to be positive. And when the structure is rigid, this idea that you have a function which is always positive is not so easy to satisfy as it may seem. Positivity can be a very powerful constraint. And that's the thing we want to do today. And one example that actually comes from a random functions, or for example, is used in finance or other things, is the matrix of correlation. So suppose I have a set of random variables and I want to know if they are correlated. I could, for example, subtract the mean value, so they have zero mean value, and I compute the correlations to see if some price or some stock is correlated with some other price. And this matrix has this following property. So if I sum over ij, some arbitrary vector xi I, aij, xi j, this is the mean value of xi I.
You seem to be
again, it's not-
writing off the bottom of the page we don't see.
Okay, now you can see.
We see the bracket AIIJ, but then you wrote something below this, which seems to be off the page.
Oh, that's okay. Then maybe I can use a different program.
Yeah, there now we see it by moving up. Okay, good. Yeah, but now we only see it.
But let me see, I can use a different program to write. Let me check.
So the next equation on the right-hand side is going off to the right and beyond the view. Oh, there. Oh, that's good. Now we see it.
Yes, I mean, I could use a different program to draw, but this is just from Zoom, so I thought it might be good. But, well, if it happens again, I will try a different program.
Well, again, now you're writing still to the right off our view.
Oh, okay, let me,
But, you know,
let me see this.
your canvas seems to be much larger than our view.
Yeah, no, for me, I see it in the screen, but okay, so this is a different program. Let's see if it works. So can you see now?
Yes, that's fine.
Okay, let me know if it goes out. Sorry about that. So if I have a vector xi I and I sum like this with this matrix of correlations, I get this is the mean value of xi I xi, xi j xj, sum over I and j. So is this thing square, and therefore this is always positive. So if I have a matrix that contracted with two vectors, the same vector is always positive, this matrix by definition is a positive semi-definite. So here we have a positive quantity, and in finance or engineering or something, if they have they measure some of these correlations and they are missing some others, then you can have constraints on the correlations that you are missing from the fact that the matrix is positive definite. So the entries can be negative or positive, but the whole matrix has to be positive semi-definite. So hopefully, yeah, the screen I have from here to here, hopefully all that is, and this is the top.
Yep, perfect.
Okay. So now the example that I want to describe today is the so-called single plaquette model or single matrix model, and also is the two-dimensional lattice QCD. And this was solved by Gross-Witten and by Vadia in the 80s, so analytically, so it's not new. but I want to show numerically how we can solve it. This gave rise to some, well, first we wrote a paper with a student applying this to lattice QCD to try to compute the expectation value of Wilson loops. There are been some new developments. Henry Lin in 2020 extended these ideas to many matrices, to models, matrix model with several matrices. Kazakov and Zheng, like Zechuan Zheng is going to give a talk next week about this and greatly improve our ideas for the case of QCD. But today I just want to give an introduction, and for that I'm going to use a single plaquette model. This is determined by a partition function, which is the integral over all SUN matrices. So these are unitary matrices with determinant 1, n by n, and they have an action which is n is the size of the matrices. Lambda is like a coupling, like a Toft coupling, acts like a temperature, and the action is simple trace of U plus U dagger. So this morning, Professor Hasselflat, she gave an introduction, and in this case, we can think of a single plaquette, and in each side you have a unitary matrix, and this is U is the product of the 4 matrices. So that's the only variable we have. So this is in SUN. And with this action, we want to compute the expectation value of what in this case will be Wilson loops. But since you have a plaquette, you can only go around the plaquette, let's say n times. This is n, and that by definition is the expectation value, one over the partition function of a trace of U to the n. And the action is this n over 2 lambda trace of U plus U dagger. So we want to compute this Wn, and we're going to do that numerically, although, as I mentioned, Gross-Witten and Vadia computed this, and for the single plaquette, which sometimes we call U, the result was that this is 1 minus lambda divided by 2 when lambda is less or equal than 1, and is 1 over 2 lambda when lambda is greater or equal than 1. So if I draw this, is 1 here, and it's a straight line, and there's the hyperbola. So there is a phase transition. The phase transition, one can do derivative here, and you see that is third order. So this is Gross-Witten. That's from the 80s. Okay, so first, what I want to describe is what's the positivity here. So we said that we want to use positivity. So if I have an arbitrary matrix A, we know that if I take the trace of A dagger A, and one can very easily compute, this is the sum over all elements. This is a arbitrary complex matrix, the sum of the modulus square of all the components, and that's obviously positive. So here we're gonna use this matrix A that I can construct by making linear combinations of the U to the n. So U is my unitary matrix of SUN, and I make arbitrary linear combination. These are arbitrary complex numbers. And from here, I see that the trace of sum over n and m of C conjugate m Cn U dagger to the power m. U to the n has to be positive for any C because of this, or any U from the condition that we have up here. And the expectation value of something positive is always positive. If I do the expectation value with the action that we had before. So here we conclude that the sum over n and m from 0 to L of C conjugate M CM. And this is unitary, so this will be U to the N minus M. And then I will get trace of U to the, well, expectation value. Well, let's write it, trace expectation value with the understanding that U inverse U minus 1 is just the dagger because it's unitary. This is always positive, but if I divide by N, this thing here is just the Wilson loop, what we call Wilson loop N minus M modulus. So W plus 2 and minus 2 have the same value. They are conjugate of each other, but they are real. And so that means that if I go ahead and write the following matrix, which let's call it rho, and I put W0, which will be just 1 in the diagonal, then I put W1, W2, W3, and so all the first diagonal is W1, so this is W0, this is W2, W3, W2, so the diagonal is W0, then W1, then W2, and I can keep going up to any arbitrary L. This matrix is positive definite. And that's the condition of positivity that you have in this particular system. And that extends to other Wilson loops, as we're going to see in the later. In particular, W0 is just trace of U to the 0, so it's 1 over N trace of identity, so it's just 1. And so example, if I look at arbitrary minors here, you will see that I can take Wn, Wn1, and that is should be positive definite, which means that the modulus of Wn is always less or equal than 1, which is correct for a unitary matrix. All the eigenvalues have modulus 1, so the mean value will be less or equal than 1 of the trace divided by N. Okay, so positivity is good, but it's not enough to obviously solve this problem. So the next ingredient that we need is an equation for these Wilson loops, and that's the so-called loop equation. So I'm going perhaps opposite the normal way to look at this will be to look at first at the loop equation and then use positivity, but we are emphasizing here positivity. So the next thing we're going to do is derive the loop equation, which is the Schwinger-Dyson equation for this expectation value of Wilson loops. So hopefully, once again, interrupt me if something is, well, first this is not clear, but also if you is going out of the page or anything. And for that, I'm going to take what one would call an open Wilson loop or Wilson line. So I'm going to take U to the N, but I'm not going to take the trace. I'm going to put some indices. And I'm going to average this with the action. And well, we can call this F or something. And as usual, the Schwinger-Dyson equation is derived by doing a change of variables in the integral and claiming that the integral does not depend on or has the same value if we change variables of integration. So I'm going to take U and I'm going to multiply by 1 plus I epsilon times U. And this epsilon, I'm going to take Hermitian and traceless, so that infinitesimal in such a way that U is still belongs to SUN and U dagger goes to the dagger. So okay, so I'm going to do this change of variables and I'm going to claim that the variation of this F, the integral is 0 because it's just a change of variables in the integral. The measure is invariant, just multiplying by this constant matrix. This is the hard measure of the group, so it's invariant. And I want to compute the variation of the integral. and say that it's 0. So first I want to compute variation of u to the n, and that's obvious. It's just, well, first if I rewrite it, I get 1 plus I epsilon u to the n, and then I get u 1 plus I epsilon u n minus 1, and I keep going, and I get finally u n minus 1, 1 plus I epsilon u. So if I go and write the variation, and here I'm going to write at the bottom, hopefully it's fine. So I will get an I, and then get epsilon u to the n plus u epsilon u n minus 1 plus u n minus 1 epsilon u. So that's the variation. And then I have to do the variation of the action. I don't know if, okay, so maybe so yeah, I cannot shift the page here. I have to completely change. So this is the variation. And I have to do the variation of the action here. This is a trace, so I just need to put the variation in the down here. And so let me write the variation of f is integral du e to the minus action, where there is an I, and then we have this epsilon u to the n plus u epsilon u n minus 1 plus we said n minus 1 epsilon u, and that's within this is AB. And then I have un within this is AB, and the variation of the action, which will be minus n over 2 lambda. And then we have an I because of the I epsilon that I took common factor. And then we have trace of epsilon u. And then you have the u dagger, so we have minus u dagger epsilon, but the trace, I can commute them inside the trace, so we get this, and this should be 0 for any epsilon. Now, for the students, some simple exercise will be like if I have some matrix BCD such that I contract with arbitrary traceless Hermitian matrix epsilon CD, and I always get 0. This matrix is of the form 1 over n trace B delta CD. So the only matrix that contracted with arbitrary Hermitian traceless matrix and gives 0 is proportional to the identity. And that means that I want to pull out from here, from the integral, some epsilon CD, and then I will get the expectation value of the rest. So here, remember that this part has indices AB, the first part. So I'm gonna get there delta AC UN DB. So that gives me this term. And then I will get UAC epsilon CD UN minus 1 CD. And then I will get, yeah, sorry, I'm going slowly, but I want to do some calculations, hopefully, to show how you do this, DB. And then we have minus n over 2 lambda UN AB, and here CD, so we'll get U DC, so I get trace of epsilon times U minus U dagger DC, and this should be proportional to the same, so it should be diagonal. Now the next thing is I want to solve this in the large n limit. So when n goes to infinity, and when n goes to infinity, I can drop the right-hand side on here. So I'm going to just set this to 0, and that's when n goes to infinity. That's I forgot to say, sorry about that. But this result by Gross-Witten and Badia was for n goes to infinity. I apologize for that. I forgot to say. Okay, so from this identity, sorry, this is always 0, not when n goes to infinity, sorry, it's always 0. But because it's always 0, I can remove this epsilon, and I should put the 1/n trace on the right-hand side. But when n goes to infinity, I can remove the right-hand side. So yes, so the reasoning, sorry, is when epsilon is, we contracted with epsilon, it's always 0, but in the large n limit, I can remove the epsilon without putting the trace. If you put the trace, it's still fine, but I want to do with when n goes to infinity, and I get this equal to 0. Now I want to contract with the delta AC. So I'm gonna contract delta AC, and this is gonna give me an n. This is gonna give me a trace. And I'm gonna contract with delta BD, that will give me a trace here. So I will get n from here, trace of u to the n, trace of u n minus 1, up to trace again u n minus 1, trace of u. And when I contract here, remember I'm contracting delta AC. So this u gets multiplied here, and I get trace of un plus 1 from this term. And from this term with this, I get trace of u dagger un, which is un minus 1, because u is unitary and u dagger is the inverse. So hopefully that's, I can go to the next step. So next page, sorry. And then what we get is that we're taking integral over u. Well, maybe I should, okay, I don't know if I did this. This is average, so this is inside inside this integral with the e minus s. So when I do average, what we get is when I contract, what we get is just a second. We get n average of trace of u to the n plus average of trace of u times average of trace un minus 1 plus trace of un minus 1 trace of u minus n over 2 lambda. We said trace of un plus 1 minus trace of un minus 1. All these should be 0. And if I divide by n squared, what I get is the Wilson loop Wn, because when I divide by n squared, I cancel 1n, and I get here the definition of the Wilson loop. So I get W1, Wn minus 1, plus Wn minus 1, W1, minus, I divide by n squared, I cancel this n, so we get 1 over 2 lambda. And when I divide by n here, I get the definition of Wn minus 1 minus n plus 1, n minus 1 is equal to 0. And I can rewrite this loop equation as follows. I put this on that side, and I multiply by 2 lambda. So I put this on that side, and 2 lambda Wn plus 2 lambda sum from p for p equals 1, sorry, to n wp wn minus p. And so we just derive this loop equation that relates the Wilson loops, and is clearly, I can use it as a recursion relation. So I can compute Wn plus 1 if I know all the Wilson loops with the index less than n plus 1. So I have n minus 1, 1, and here I have up to Wn. And so one can say, well, this is very easy to solve. I give some value to W1, and I go ahead and compute all the other Wilson loops. But W1 is precisely the thing we wanted to compute. That was the result of Gross, Witten, and Badia. That means that there is an infinite number of solutions to this loop equation. So I can give W1 any value, and then I can compute all the other Wilson loops. How do we compute W1? Well, we use precisely the positivity condition. So I have to find solutions to this equation. As we said, numerically is trivial. I just give some value to W1, and I can compute W up to, I mean, arbitrary, well, I don't know, 500,000 or whatever by doing this recursion. But I want to find solutions that satisfy that this particular matrix. What we said, I put W0 in the diagonal, then W1 in the first of diagonal, and I keep going like this. This matrix should be positive definite. So when we did this, we were quite nicely surprised that if you put, for example, 8 by 8 matrix, which is very small, you get basically completely determined W1. So W1 has a range of values within which this matrix is positive definite. So the matrix is computed by W0 is 1, W1 is some arbitrary value that I give, and between -1 and 1. And W2 is determined by the loop equation, W3, let's say up to W8. And the requirement that this is positive restricts the value of W1 so much that you get very precisely the answer that you know. So that's the part I wanted to discuss in the Blackboard. Where do we go from there? So this, as I mentioned, in 2020, Henry Lin, I found a way to solve matrix models numerically by using this idea. So you can have more than one matrix. They can be Hermitian instead of unitary. They can have a more complicated action like trace of m squared, m to the fourth, and so on. But by writing the loop equations and writing and there can be more than one matrix, as I said, and writing the corresponding consistency conditions, the positivity conditions, you find that you restrict so much the numerical solution that you can compute with many digits of precision the result. And in that way, he solved, and there were many more papers after that. He solved certain matrix models that have no analytic solution. The other thing is we did with my student Peter Anderson, and that was what we wrote in that paper, is to apply this to lattice QCD in 3+1 dimensions and try to see if we can compute the Wilson loop the Wilson loops in that case. And we did some ideas that I'm going to describe now, but as I mentioned, this was greatly improved recently in this year by Vladimir Kazakov and Szechuan Zheng, but I'm not going to describe that because Zheng is going to give a talk next week, so I'm not going to try to do his talk, so I'm going to just describe what we did. So let me switch gears now. Any questions up to here? Because I'm going to start with something else now.
Any questions? I don't see any, I guess. Go ahead.
Yeah, okay. So I'm
I have a question.
Wait. Did someone get a question?
Could you give a,
Yes.
is there a geometric way to understand this loop equation?
No, I don't know. What do you mean by geometry? There is
Something intuitive, like why should I expect a equation
well, there
like
is
that?
a nice way to describe it that I'm gonna do now, but it's not. I don't know if. Okay, let me do this. Okay, let me see. So can you see my slides? I'm sharing. Am I sharing the slides?
Yes.
Okay, so there is a way to describe the loop equation. I don't know if this is what you were asking. The action has trace of U, and trace of U is a plaquette. Can you see the cursor where I'm pointing at? Or
Yep.
So if you have a Wilson loop, in this case, well, I'm gonna go back to this, but this is just to answer the question. If you have a Wilson loop that goes through a certain link, what you do is for all the Wilson loops, the action is written in terms of Wilson loops, and in this case, I only have a plaquette. What you do, you put the plaquette touching the Wilson loop, and then you connect it. So instead of going through the link, you go first through the plaquette and then through the link, and you subtract the same by putting the plaquette with the opposite orientation. So you're gonna go back and forth here, so you cancel it and you get this. And then there is a self-intersection term, which in this case, self-intersection means you go through the link, so the same link, not through the same node, but through the same link twice. If you go twice in the same direction, you split the Wilson loop in two like this. And if you go through the same link, this is just this, your Wilson loop goes back and forth on a link, you split it in two. And the loop equation just has this part, which is depends on the action. So it's connect all the Wilson loops you have in the action with your Wilson loop in this form. And then you have the self-intersection. I don't know, this is more intuitive to write, but it's not the derivation. I don't know if that you were asking, if this answered your question, but this is a naive, a simple way to describe it geometrically. And in the single plaquette, your Wilson loop was going around the plaquette just many times. So you have all these self-intersections, which was this sum of W0 to W, so W1, Wn minus 1. That's the self-intersection term. And then connected with an extra plaquette give you Wn plus 1 minus Wn minus 1. So that's, I wouldn't say a geometric derivation, but it's a geometric description probably of the Wilson loop. I don't know if that answers it or not.
Hello?
Yes.
Yes.
Thank you. So just to confirm, like, so does this also tell you how to go if you have some matter insertion or something like that? Like other insertions in the lattice, not just pure Wilson lines? Because the picture
Okay.
seems to be more
What I
intuitive
said
to
is
visualize.
sometimes in the action you could have a square, so a plaquette, but you could have a rectangle. So that's a so-called improved actions that tells you how to do that. Now, if you have matter, you have open Wilson lines, and you could, yeah, I think you should have a loop equation. I didn't look at that, sorry. But with matter, you have not only closed Wilson loops, but also open lines. So what I said is more for generic, more generic action, but still for pure Yang-Mills.
Slide, just historical.
Yes,
not
that I
this
don't
one.
have the, yeah, I cannot go back to that. Or
Okay.
maybe I can, yes, sorry. I can.
No, the point is that these different signs that you talked about were not present in the equations written by Migdal and Makenko and by Eguchi. I think these signs and the way the Wilson loop traverses parallel or anti-parallel to the
Okay, in this
links,
slide, sorry.
those signs, I think they were first derived by Forster and in my paper, actually. I don't know whether you know about that. But,
sorry, no. Okay,
I have
maybe
spent a while, yes. Sorry.
how are you? Yes, yeah, I think we
I'm
met, yeah.
okay. I just wanted to make this point, actually. These signs are very important, as you know very well. So
Yes. Without that, it doesn't work.
that's right.
Okay.
Okay,
So,
just a little comment I wanted to make. Yeah, thank you.
okay. Thank you for the questions. And so, okay, this is more just going faster over the results than derivations like I was doing up to now. Hopefully the derivations give an idea of how this works. This part then is, based on this paper with my student Peter, as I mentioned. There are some new results by Kazakov and Zeng this year, and Henry Ling had this paper about the matrix model, which I'm not going. So I'm not going to go into these papers, but hopefully there will be some talks next week. There is a lot of new developments here. So these are like basic references for the students if you want to see the idea. So what's the main motivation?
Oh,
So
I guess
yes.
I have a question. Can you take the large n limit of these equations and get simplified equations?
Sorry, yeah, I shouldn't have explained. This is always a larger limit. So
Oh, it's
what
all
I
in the
did
large
is,
n.
yes, because if not, you have a mean value of trace of u squared, let's say trace of un minus 2,
Sure.
and in the
right.
larger limit, it factorizes in the product of the two traces. Yes, so
Oh,
mean value of each trace. Sorry about that.
So it's only
Yes, so
larger
what
limit.
I,
So,
yes.
so
So this method is to solve the larger limit of the matrix models or the lattice pure Yang-Mills.
okay.
Yes, so I should have emphasized that more. So yes, that's Henry Lin solved the matrix models in the larger limit, and also with Peter and Volodya and Sichuan solved always study larger limit, which has its own interest, and also numerically it's harder to approach. Although in many of these situations we did numerical simulations of the lattice, and SU10 already gives something like the larger limit, but
So
still
that's
you
why.
need.
So that's why
Yeah.
you were regarding powers of U to be spatial Wilson loops in the large n limit.
Well, here is a single plaquette, so you go around the plaquette, and the only thing you have is that the mean value of the product of two traces is the mean value of the product of the mean values. That's what I was using at some point. Otherwise, you get Wilson loops which have many disconnected contours.
Uh-huh.
But now I'm gonna do what you are saying, which is doing higher dimension where you have more interesting Wilson loops. That's okay.
Yeah, sure. Go ahead.
Okay, so the one motivation is if you can define a gauge theory purely in terms of gauge invariant quantities. So that's always an idea that gauge symmetry only tell you there is a redundancy in the degrees of freedom because you want to have a manifestly Lorentz invariant theory, so you add some polarizations to the photon or to the gluon. But then you have the gauge symmetry that removes it, but there should be a formulation perhaps purely in terms of gauge invariant quantities. We know that's possible, for example, from the ADS-CFT correspondence, where you have a dual string theory, which doesn't have any gauge symmetry, at least in the sense of the SUN. So the strings describes only gauge invariant quantities. But the original idea, I think, already goes back to Wilson or maybe other people, is that you should be able to describe the gauge theory just in terms of Wilson loops. So there should be a theory of Wilson loops where you have an equation that you can solve, and from there you can compute the Wilson loops. And that's a basic equation, is the loop equation of Migdal and Makenko. And I guess Spencer Vadia there was clarifying, yes, the other people, or Forster and himself, Maevadia and others also wrote this type of equations, and with perhaps some more correctly, I guess. But okay, so what is a lattice gauge theory? So I guess this morning we had a nice talk, and I couldn't attend all the talk because here is a bit during the night, but you have a lattice which is higher dimensional. I'm just drawing 2 dimensions for simplicity, And in each link, you have a unitary matrix. So now we have a lot of unitary matrices. And I have an action, which is a simple Wilson action. You multiply the matrices in a plaquette, which is called just a little square. You multiply these 4 matrices. You take the trace, and then you average over integrating overall all matrices in the links. And you sum the you integrate, you multiply for each plaquette and you sum overall plaquettes, and that gives you the so-called Wilson action. So the action usually goes in terms of a Wilson loop. The Wilson loop is a more general closed path in the lattice, and for each path you multiply all the matrices associated with all the links, and you take the trace. And the plaquette is, well, the simplest Wilson loop is just a point, but the plaquette is the next, or the simplest non-trivial loop. So usually the action is written in terms of Wilson loops themselves. So one is a plaquette, but you could take a rectangle or other Wilson loops. Once again, lambda is a Toft coupling, and depending on the dimension, this system behaves differently. So for 2 dimensions, as we say, there is a 3rd order phase transition. For the 3 dimensions, there is also presumably a 3rd order transition, which was found by Tepper numerically. And for 4 dimensions, which is the interest for the real world, there is a 1st order transition. And I just citing this paper, which is one of the most recent, where they study the Larsen limit. Again, this is all the Larsen limit. And the purpose is to compute the expectation value of the Wilson loop using this action. And as I was describing, the first thing you can do is to write the loop equation. And the loop equation comes from connecting the Wilson loop that you want to compute, go through some link. So here will be, suppose this link. So I will have coming here and then going around this plaquette and keep going, or going like a U shape and keep going. But then I have to connect it also on this side, and I have to connect to every single link of my Wilson loop. And that gives me a list of Wilson loop with a plus and the other with a minus. And then I have the self-intersection terms. So for example, this Wilson loop that has no self-intersection, but self-intersection is when you go through the same link twice, either the same direction or opposite. And then the Wilson loop splits in 2, and this is where the Larsen limit appears, because you have the expectation value of this, and that becomes the product of the expectation values in the Larsen limit. And so you have a term which depends on the action, which is like sort of Laplacian. And then you have a self-intersection. The self-intersection is the non-linear part. If the loop doesn't self-intersect, then you only have a linear equation. So what you can try to do to solve this loop equation, you make a list of Wilson loops. For example, here I'm drawing in 3 dimensions, but you have to do 4 dimensions. And so you have the plaquette, the rectangle, then like a chair, many Wilson loops. And you kind of classify them, let's say Wilson loop 1, 2, 3, you order them in some arbitrary manner, and then you get equations among them. So these are just 2 equations you can write, but you get a very large number of equations. The other thing, in higher dimension, you have, when you increase the length of the Wilson loop, the number of Wilson loops that you get increases really fast. So it's hard to deal with. And the other problem that you have is that we said that the loop equations, you should connect it with a plaquette. And that means that the Wilson loop, the length increases by 4. So if I write the loop equation for a loop of length L, typically the loop equation involves Wilson loops with length L plus 4, that there are many more, and that I don't know. Then that means that if I take the limit of the length of the Wilson loop goes to infinity, this limit is not well defined, because you have many more loops than equations. So I have one equation for each loop of length L, but they involve Wilson loops of length L plus 4, which are many more. So I have always more Wilson loops than equations. And that means that there is no unique solution, there is an infinite number of solutions, and the limit is not well defined mathematically. However, that's where we said, okay, we go back to what I was explaining before. So we shouldn't take arbitrary solution. We know that even in 2 dimensions, a single plaquette, there is infinite number of solutions. What we have to do is to impose this positivity condition. And imposing this positivity condition is what people call the bootstrap method. So what are the positivity conditions now? So we said before we had a simple way to derive it, and here we can extend it to higher dimensions. So suppose I have, I don't know if you have do you have this thing here on top? No. Okay. So I don't know if you can see the whole figure, but I have an initial point and a final point, xi and xf on the lattice, and I draw a bunch of open lines that go from the initial point to the final point. So I have the red line, purple, green, and black, let's say. And for each line, I multiply the matrices associated with those links. And that matrix I call U superscript L, and I put L or capital L number of these open lines, like some arbitrary number, and the more I put, the more constraints I get. And then I make an arbitrary linear combination of all these open lines, and I said trace A dagger A is positive, so this trace is positive, and the mean value of this is positive, because the mean value of any positive quantity is always positive. But what is this Wilson loop? This trace. This trace is I'm going from xi to xf along open Wilson line L prime, and then I take the dagger, but the dagger is like going backwards. So it means I go along L prime and I come back along L for all the L primes and L. So this trace describes a Wilson loop, which is closed and goes from I to F along, let's say, path L prime and come back along L. So this, once again, is a matrix of Wilson loop. It's a matrix of Wilson loops that is positive definite. Sorry. It's not as simple as before. It's not W0, W1, W2. But it's, sorry, with this COVID, I still have some cough fits from time to time. But it's a matrix where each entry is the expectation value of a Wilson loop. One interesting way to understand this is to see that I have, well, obviously some color indices. The matrices have some indices. And taking the trace is just summing over A and B this contraction. So I can think that if I have the open Wilson lines, I have matrices with indices A and B. But after I contract them, I have a much smaller set of numbers. So I'm removing the information over the color indices. So this row, I can think of it as a reduced density matrix that removes the information of the colors, and I can associate an entropy associated with the Wilson loops in the usual way of taking trace of row log row. And this behaves as some sort of entropy of the system, and I have here a plot how this entropy depends on lambda, and this entropy now is evaluated on the lattice simulation. And another important thing that is more or less apparent in the picture is that I'm taking row by taking different initial and final points. For example, row 4 is taking the initial point to be 0 and the final point to be 4, and taking paths from 0 to 4 or 0 to 3, 0 to 2, and all the density matrices have more or less the same entropy, and the entropy has a jump at the position of the first order phase transition. So this is just an aside, which is not relevant for our thing, but since the matrix rho is positive definite and has trace 1 by normalization, then one can define this kind of entropy. Another interesting thing is that this matrix should be positive semi-definite, but there could be some situations where it has a 0 eigenvalue. So the eigenvalue should be positive of 0 or 0, but they could have a 0 eigenvalue. And if it has a 0 eigenvalue, that means for a particular vector C0, this is 0, so that means that there is a 0 eigenvalue. But then this particular matrix that I construct like before, but not for arbitrary C, but for the 0 eigenvalue, the trace of a dagger is 0, and that means that this open Wilson lines, so there is a combination of Wilson lines which identically vanish. And if that's true, then I can close it with an arbitrary, so I have a linear combination of these guys, which is 0. I can close it with an arbitrary path, and I take expectation value and trace, and I get 0. That means that I get an infinite number of equations for all the other Wilson loops. So, so this is a very special situation where this matrix has a 0 eigenvalue. One example is if the free theory where the expectation value of the single plaquette is 1. If I put 1, 1, 1, 1, I get a 0 eigenvalue. And one can derive from there that all the Wilson loops are 1, which is correct for the free theory. But one thing that turns out to be interesting is that in the weak coupling limit, which is relevant for QCD, so QCD we are in the weak coupling limit because this coupling is at the lattice level, so the theory is asymptotically free. So at the lattice level, which is the UV region, the coupling should be small. So in the weak coupling limit, you are very close. The eigenvalues are very close to B0. So you have these very large sets of equations. Anyway, so now I want to show you the actual results of what I was saying before. So we start with the 2D case, which is Gross-Witten and okay, body I forgot to put here, sorry, but then you have a matrix of Wilson loops, and if I take a matrix 4 by 4 and I plot the allowed values of the plaquette as a function of the coupling, you can see that between these two blue lines, if I take the value of the plaquette between this line and this line, and then I recursively compute all the Haiger-Wilson loops, only between these two lines is the matrix 4 by 4 positive definite. But if I do 6 by 6 or 8 by 8, you see that the allowed values that keep those matrices positive is much smaller. And if the exact solution is this dashed line, so if instead of 8 by 8, I go, let's say 16 by 16, you just cannot distinguish the allowed region from the exact solution. This exact solution is a straight line from up to 1, and then it's a hyperbola, as we said before. But this is what I was saying once again, there is an infinite number of solutions to the loop equation, but by putting an arbitrary value, let's say here, of the plaquette, then recursively I can compute all the Wilson loops, but only when I take from between these two lines is the matrix positive definite. And the larger the matrix I take, the much more restrictive the solution. So this is what we did now. This is more original for the 3D case. We did this numerical simulation. That's not original. Many people did that, but this is the dots. The red dots are the, I think, SU10. We solve numerically for a 8 by 8 lattice or something like that. And these are the bounds. So they're a completely different method. The color lines are by using the positivity conditions. Now, it does not restrict the solution that much, but it kind of it's not as good as 2 dimensions, but it's starting to look interesting. And as I said, this year, Kazakov and Zeng, they greatly improved this idea, but I'm not going to describe that paper because he's giving a talk next week. And this is in 4 dimensions. Once again, notice that at weak coupling, the solution basically matches the upper bound. And as I mentioned, you reach a bound because the matrix stops being positive definite. So when you reach a bound, you start getting a 0 eigenvalue. And that means that you have an infinite number of extra equations when you get that. So the weak coupling region here I'm marking here is the relevant for the continuum limit. So the continuum limit happens, lambda goes to 0 in this region. And in that region, you are matching the upper bound. That means that you are having these 0 eigenmodes, 0 eigenvalues. Okay, so that's basically what I wanted to say. So it was an hour, and I don't know. I think I have extra 15 minutes. I'm not sure if those 15 minutes are for questions, or I can say a couple of more things. But basically, that's what I wanted to say today.
Thank you very much. Do we have some questions? Well, I'll start off with a question myself on this last point. When you go to weak coupling, what you expect is that there's another scale, which is the string tension, right?
Yes.
So small Wilson loops will look like they're almost free, and you'll go close to the, but that's not going to be the scaling place. You want to also see the string tension. So you have to see the size of the Wilson loop when it gets large, starts to see linear behavior as opposed to the near Coulomb behavior. So it's going to be hard for you to, I would think, to be able to see that separation between the short distance and long distance.
Yeah, that's an excellent point. So this method, we are trying to compute the plaquette, let's say. What you are saying that to understand properly QCD, you have to have that, yes, like some perturbative behavior for small Wilson loops, and you have to be able to show that big Wilson loops show confinement. Now, the loop equation is very hard for that, yeah, because you will have to have a Wilson, very long Wilson loops. Yeah, so we don't know how to look at that.
I mean, in fact, the plaquette is just a simple cutoff effect. I mean, you could change that arbitrarily by changing the action.
Yes, and well, I mean, for a given coupling, the expectation value of the plaquette is well defined, and we are trying to compute it. But as you say, that doesn't answer the question if QCD is confining or not.
Do you have a way to check asymptotic freedom at all? Because you can't do it at the cutoff. You still have to go out to see asymptotic freedom.
Yes, yes. So no, that you need to have a large Wilson loops, and that's challenging also for lattice. Although I mean, in lattice you can smear the Wilson loops, and you can compute relatively long Wilson loop by using smearing and other techniques. But no, this loop equation at the moment is not enough to answer the questions you are asking.
And it's going to become even worse because, of course, the scale depends exponentially on lambda, right? So a very small change in lambda is an exponential change in the crossover from short distance to long distance. I mean, that's what asymptotic freedom tells you. Right?
Well, yeah, you need to have some way to figure out the loop equation for long Wilson loops, and
then you have to be very carefully tuned because the correlation length is exponential in 1 over coupling squared.
Okay, yes, yes.
It's going to be very hard to, even when you do that, even in Monte Carlo, you have to be very careful to get to that region. It's a very small window, even on large lattices, to find the place where you're physically, where the box size is large enough and the lattice spacing is small enough, and it's a very small window, and it almost fixes the value of lambda. That's the reason in Monte Carlo, you'll find that almost all calculations have lambda varying by only about 10%, no matter how much they try to find it, right?
Yeah, yeah. So at the
Very
moment,
small.
so we need to improve this is one thing that, okay, I'm not sure if it's not directly related to you are asking, but one way that people compute Wilson loops, even in Monte Carlo, because the expectation value for large Wilson loop is very small, as you say, because of the
what I'm saying
exponential.
is that there's a small value of lambda, which is between the strong coupling region and the unconfined region. You have to get to that. There's a very fast shift. And you have to be right at that position, even on a lattice that is, 32 by 32 or 100 by 100. And if you're not there, you don't see the physics at all. You see either strong coupling on one side, or you see actually a free theory on the other side. So there's going to be some critical value of lambda that you have to sit at. Looking at the whole window in lambda is not giving you the physical limit.
Yes,
I mean,
yes. I mean,
I understand the problem is technically complicated, but eventually that's the physics.
yeah. If you want to understand the physics of confinement, you have to be able to go to large Wilson loops. No, one idea was that so because the Wilson loops are very small for large size, even in the lattice, they are in some sense impossible to compute. But what you do this smearing, and one way to do is this gradient flow. So you have a configuration of the lattice that you generate by Monte Carlo, and then you flow it, as they call it. Well, I guess you know this very well, but for the other guys, yeah.
But maybe a test of an easier test of it would be to stay in strong coupling and try to compare your assumptions of positivity with the strong coupling expansion, with the strong coupling Monte Carlo. So then you would be.
I know the strong coupling, the Wilson loop was very, yeah, for that. No, the positivity conditions actually are good. Do something here. At strong coupling, you are kind of well inside the window. So the positivity conditions are more restrictive at weak coupling. And for strong coupling, you should, yeah.
Is strong coupling there easier or harder? That's what I'm trying to understand.
Well, strong coupling, you can do the strong coupling expansion and compute this Wilson.
So
This
you're consistent with the strong coupling expansion. Okay, I see.
Yeah, I mean, these lines are the strong coupling expansion and perturbation theory,
Okay, I understand. So it's strong
the lines, but all these are finite ends. So this is infinite end. The lines are strict bounds. If you want, these are strict mathematical bounds for infinite end. Where this is just a not just, but it's a Monte Carlo simulation, and the strong coupling expansion and the weak coupling expansion and the solid black lines. So in the strong coupling, the bounds are not, I mean, they don't restrict as much as weak coupling. At weak coupling, you seem to match the upper bound. So these positivity conditions are more important at weak coupling, where the Wilson loops are close to 1. At strong coupling, the Wilson loops are very small, and they all except the diagonal, which is 1. All the others are very small, and the matrix is always positive definite. But at weak coupling is where you can go away, because all the Wilson loops are around 1, and you can get this.
Okay, that makes sense. Actually, the bound, you're very close to the bounds, aren't you?
Yes, it's very close. I have some, oops.
Anyway, I've asked too many questions. Let me see if some other people.
No, it's very good, because, yeah, no, those are the things we don't know. So I have sorry, I didn't put it. Maybe I have the actual numbers here, but the numbers are very close. Yes. So
you're jogging my memory, but at one point or other, I think I did the exact one link integral and was in sort of earlier version of Gross and Witten.
Oh, okay.
And then they did a better job. So I'm not as usual.
But no, that's good. Yeah, no,
but it was nice to see some of that coming back. Yeah. But it's gone much farther than when I dipped my tiny finger into it. Thank you. Anybody else have questions?
Sorry, no, I wanted to mention something about what you said, which is tangentially related, which is this gradient flow. So people, one way to compute the Wilson loop is you have several configurations of the lattice, which the value of the matrices fluctuate widely, let's say from one to the other, but then you smooth the configurations out by doing what's called the gradient flow. So you get, then the Wilson loops are easier to compute numerically because you have less fluctuations. And the only thing I wanted to mention is that the operator that does this smoothing out, which is called the gradient flow, is the same operator that appears in the loop equation. So when you do the loop, so basically you flow with the operator that appears in the loop equation, and that gives you, but the flowed Wilson loops obey the same positivity conditions. So in principle, you have an infinite number of positivity conditions for the flowed Wilson loops, but that could be a way to approach large Wilson loops, but we haven't worked on that.
So you saying the
So much.
same equations hold for the Wilson loops after they've flown?
No, the same positivity conditions, because you do the flow and you get a new configuration which is smoother, and you compute the Wilson loops there. But the
Oh, I see. Okay,
condition,
fine. Yeah.
the positivity condition didn't depend on which configuration you had. So yes, the flowed Wilson loops obey the same positivity conditions.
Oh, so that's okay. So you just do it on that lattice. And now,
Yeah, in the flow lattice, the expectation values of the Wilson loop should still obey the same positivity conditions, because they didn't depend on it's just for arbitrary lattice, the mean value should obey the positivity
that
condition.
might allow you to find the scale then of the lambda parameter from the Wilson flow. That's one of the, I don't know. It's an interesting question. You might get some more closer to what physics you're looking for.
Yes, that was the idea, but we didn't work on that anymore. So yeah, but it
I
would be
think-
nice to revisit that.
Oh, it's
yeah.
that sounds very interesting. I can't think through, even if I weren't jet lagged, but that sounds like you might be able to get closer to what window you should be looking at. Yeah.
Yes.
Yeah, that's interesting.
Hi, Martin. This is David Shake, and
Oh, how are
I
you?
just
Yeah. Sorry, I
also jet
couldn't be
lagged,
there.
so this might not make much sense, but it's a small postscript to what Rich was saying earlier on your slide 13 here. What came to my mind because I looked up that reference, Campestrini in '99, because I didn't recognize it, and I noticed that that fellow was actually working with the twisted Iguchi-Kawai way of setting up these gauge theories, where there's a large N and it's all shoved down onto a single lattice site, and all of the degrees of freedom are in the color degrees of freedom. And that's reminding me of some of the other sort of Iguchi-Kawai reduction stuff that people have done, where they look at those long distance quantities like meson spectrum or possibly string tension. I'm not sure about that, even though they formally have just this single site. I don't know enough about it to say how sensible that is, but I think Antonio Gonzalez Arroyo is meant to be here later in the program and might be able to say if there are any points of intersection that would be easier for you in that way of approaching things, rather than trying to push to the large Wilson loops to get that twisted reduction as a way of proceeding.
Oh yeah, I didn't study that much. Yeah, as you say, I mean, I have that citation because it seems to be the latest large N results. But yeah, his method is different, and we didn't look at loop equation in that method. So maybe that might be an interesting idea.
I'm not sure I can shed light on it, but I actually had the same question. In Iguchi-Kawai, I mean, you have to be very careful about this question of the right phase, but it's been worked on very carefully by Herbert Neuberg and Mariana. But the main point is that you really have a single matrix. I thought you were doing that at first. You have a single matrix, and when you you have 4 single matrices, one in each direction, right? And then by the multiplication of these matrices, they become in the large limit, large Wilson loops. But you don't have other matrices. So it might actually be possible for you to really simplify your thing. I mean, that's the basic idea. The Iguchi-Kawai matrix at large N becomes a big matrix. And it combines gauged fields with shift operators. And therefore, to get a Wilson, for example, to get an N by N Wilson loop in large N, you simply multiply this large matrix, L times or N times by N times and so on around, and that gives you a measure of a larger Wilson loop. There's a tricky thing of making sure you don't. What's the problem? You get in the wrong phase.
There is one thing, this master field should be a large n by n matrix, but that's not the same thing, right? Or is this what you're saying?
It's still a unitary matrix. So this is really off, just speculating, but it sounds like a lot of your formalism would continue to apply. They even managed to put in quenched quarks this way. It's tricky, but I have the feeling it might be a way for you to reduce your problem to get some physics without having different matrices.
Okay, no, that's interesting. Yeah, I didn't think about that.
And
That's
in fact, I mean, when people say the QCD string doesn't exist, actually, a partial part of the QCD string does exist as a matrix model, which is one of the way to look at string theory. So this is it's a very important thing, which I think is often neglected. Part of the QCD string is numerically calculatable within the matrix model of the UBGY. And you can get some very accurate answers in principle for also meson states, the Cairo-Lagrangian, and the Wilson loops. It's never been done at huge exascale resources to get an accurate answer, but there are some things that you can actually calculate beside the usual thing of large n. I mean, it's quite a, and the most serious attempt was done by a sort of hybrid method by Herbert Neuberger and what's the Narayana? I can't pronounce his name correct. Yeah, Rajamani Narayana. In this country, I should at least make practice on that. Okay, and they did a kind of partial thing where they to stay in the right phase, they had large matrices but not one matrix. But that was just a fix. But I would think this is really naive. But as I see your algebra, I'm just wondering whether you couldn't apply it to that context.
yeah, that sounds very interesting. Yeah,
It's
you should
certainly
look
worth
at
looking
that.
at. I mean,
yes,
you
yes.
probably within a day would say they're a completely stupid idea that I gave you, but maybe you wouldn't.
No, it sounds good. No, I didn't think about those things. And
But
we got, I mean, to be honest, we got a bit stuck here. And as I said, Vladia Kazakov and
I mean,
his student, postdoc, they did improve a lot, but I think still there is a lot to
it
be
really is like
desired.
matrix
Yeah.
model string theory. I mean, there were two things they could do. They could do repeated products of these things to get large Wilson loops. And then they also realized that they could put quarks in the thing by simply taking it and changing the boundary condition when they ran out of this small lattice. And then they could piece them together and let the quark go through a large, and they could make, for example, they could look at the pion and see, for example, what the mass dependence of the pion mass was for the Cairo-Lagrangian at infinite n, which is actually simpler because even the Cairo-Lagrangian at infinite n has no loops. So they really were beginning, I think they stopped this and had other better things to do in their life, but they were actually be able to find data of what the large n QCD string had to be in certain regions. So I thought it was somebody who had the strength, it would be an interesting problem. Anyway, thanks very much. I took a lot of questions myself, which was probably the wrong thing as moderator. Does somebody else have questions? Yes. Sure.
Yeah. So my question is this L dependence the same in higher windings of this Wilson loop? I mean, when I worked
Winding, you
with,
said.
yeah, I mean, when I worked with this Monte Carlo, at least for the 2D case, what I saw that at least in the strong coupling regime, we need very large n to reach to the analytical results. So
Sorry, you are saying N like the SUN or the L, the length?
so yeah, n as SUN.
Well, I don't know in 2D, and in higher dimension, I think SU10 roughly can be considered close to infinite n. I didn't do simulations for just a single plaquette. So you say you need a, well, so you're saying the Monte Carlo requires large n, or?
Yeah, for higher windings of the Wilson loop.
Ah, okay. So yeah, I don't know then. Yeah, in higher dimensions, these higher winding, they are not that relevant. They are only very few of. But of course, if you have a single plaquette, the only thing you have is higher winding. But I'm not sure this higher winding plays a significant role in the higher dimension, like 4D. But yeah, I didn't know that in 2D you needed. Because of that, you needed to simulate large N. That's interesting, but
Again, I may be completely wrong, but I think is back with the stuff that I was doing, it's an exact solution to the one matrix integral at infinite N. It's one of these matrix models of results. I think there's an
yes,
exact solution.
well, the single plaquette can be solved analytically by one way is to find the distribution of
There's
eigenvalues.
differential equations for the spectrum and so on. I can't remember what they are, but you know the exact answer, so you can find it out.
Yes, but that only in the for the Wilson action, the simple one. But if you complicate the action or then
Wilson action's fine. I mean, there's no need.
yes,
for
yes. No,
physical-
what I'm saying is that, for example, Henry Lin has these new results of other actions and for.
Yeah, no, that would then have to start all over again. Yes, of course.
But yeah, so the 2D is known exactly, but I think what the question was that if you try to do it numerically, it's much harder because of the higher winding loops around the plaquette.
I'm just saying you could
No.
find out what the corrections were in 1/n, and then know whether you were doing a good job.
Yeah, okay. I think Henry Lin has a way to compute the 1/n corrections using these methods. I don't know how to do that in this lattice, but yeah, that's another thing one can try to compute. In the loop equation has 1/n corrections in principle, and one can check how much is that satisfied or something. But I didn't do in any systematic study of 1/n.
So maybe we continue after tea. So we can take 15 minutes tea break, and next is for discussions on lectures after tea break.
Okay, thank you
Yes.
very much.
So let's
Then I will
thank
stay
Martin.
for